Dude, stop daydreaming. You're filming, man.
Hey, sorry. Anyway, have you heard about this very famous German chemist, August Kekule?
August what? Kekule?
Yeah.
Dude, he's German. It's Kekule. Can you respect the dead? Please, man.
Okay, cool story, bro. Anyway, there's this very famous urban legend about him. While trying to work out a structure that could explain the peculiar properties of benzene, he had a daydream on top of a bus, whereby he dreamt that a snake was chasing around its own tail. And from there, he came up with the structure of benzene, which is basically a ring of 6 carbon atoms with alternating single and double bonds.
Okay, so a ring, 6 carbon atoms, it looks like this then. So you have a ring, you have 6 carbon atoms, and you said alternating double bond, right? So double bonds, it could be between 4 and 5, so carbons 4 and 5, 1 and 6, and 3 and 2. But here's the thing, it could also be the 3 double bonds, it could be between 3 and 4, 5 and 6, and 2 and 1. And that's why Kekule was really, he was baffled, because he was thinking, where should my double bonds be? And that's why when he was daydreaming on the bus, he was like, eureka, right? He said, okay, since the double bonds are everywhere, why don't I just treat it like a snake eating its own tail? In that sense where, since the double bonds are everywhere, right guys? It's everywhere, so why don't we say it like that? The double bonds are here, 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 and here. And it forms a ring. And that's why that snake eating its own tail. Cool, guys? Okay.
I have a question.
What's
Do
up?
we need to draw the snake in the exam?
Yes.
Okay.
Hey guys, so benzene ring, right? So we just talked about it. Benzene, C6H6, and what Kekule mentioned in his daydream or in his paper is that 6 carbon atoms, right? And you have alternating double bonds here.
Bond.
Double.
Bond.
Now, Yap Chen, you're going to be my student today. I'm going to ask you a question.
I'm a student.
Yes, you're a student, first time. So this carbon atom here, can you tell me how many bond pairs, how many lone pairs?
3 bond pairs, 0 lone pairs.
Hey, very good, right? 3 bond pairs, 0 lone pairs. Hybridization, please.
sp2?
Very good, sp2. So here's the thing, is sp2 hybridized and each of the carbon atoms, they're all identical, so they're all sp2, okay guys? Now, sp2 hybridized, and I hope you guys can remember, if you're sp2 hybridized, it means you have 3 sp2 hybrid orbitals. Now here's the thing, listen in, this is the part that's important, right? You have this 2p unhybridized orbital. Now Yap Chen, can you just tell me why is it so important? Why is that 2p so crucial?
Well, this 2p orbital is going to use to form the pi bond.
Exactly, right? P stands for pi, okay? That P here literally stands for pi. So you can tell yourself, each carbon here has an empty 2p, each carbon here has a 2p orbital, and I'm going to draw this with you guys. Go to the carbon atoms, each of them, there's this 2p orbital, like that, and it forms that double bond that you see there. So do this on your paper with me. Go to that p orbital there. You can do this with me. They are parallel to each other. They're going to sideway overlap to form that double bond here. Sideway overlap, double bond, perfect. Sideway overlap, perfect. Sideway overlap, perfect. And we have 3 double bonds. Now here's the part where Kekule got really fed up, because he was thinking, and I'm going to jump right into this. So if there are p orbitals everywhere, so this double bond, these 2p orbitals overlap, likewise. Now here comes the problem, Yap Chen.
Yeah.
So don't you think there should be a double bond here as well?
Yeah.
There should be, right?
Yeah.
Because the p orbitals, again guys, parallel, and they can sideway overlap.
Yeah.
So by right, there should be a double bond here, and double bond here.
So there's double bond everywhere?
Exactly.
Ooh.
And that's what Kekule thought. There should be double bonds everywhere. And he thought that it looks like this. So TLDR, when all these 2p orbitals sideway overlap, and they're parallel and they sideway overlap, it forms this cute little donut here. Okay? And there you have it. That is benzene. And that's why we draw benzene like this. And this is what we call resonance. Now listen in. What resonance means is this. So again, I'm a bit naggy now. Yes. Almost like our parents.
Shanice.
Yeah?
Your mouth is moving a lot like a rat. Yappa, 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 yappa. Shut it, please.
These p orbitals here, they sideway overlap, form all those double bonds, right? But tell yourself, because by right, these 2p orbitals are also parallel and they can sideway overlap. By right, there should be a double bond here, and here. Now, this idea is called resonance. There is no double bond here right now when you draw it, but by right there should be, right? So we say that these double bonds can move. And we show this movement by doing this kind of arrow pushing. Remember guys, arrow pushing means the transfer of 2 electrons, okay? So when we push arrows like that, it looks like this. There should be a double bond between here, and here, and it looks like this. Now remember guys, write this down for me. This is what you call your resonance arrow, okay? is double-headed. Take note, guys, it's double-headed. And this is how benzene looks like. It looks like this. Can you imagine, right, in exam, if you have to draw benzene like this and you have to draw it dotted, 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 oh my god, I think you'd be frustrated.
Yeah.
How would you draw it then?
I'll draw it like an egg yolk, maybe like this.
Exactly, so much simpler. And this is how we draw benzene, right? Just a simple circle in the middle. Don't waste time doing this, okay? And that's it. So this is how benzene looks like. Now, here's where we're gonna get a bit more specific. Now, guys, understand this with me, okay? I want you to go back to this picture here, and I'm gonna focus on this carbon 1 and carbon 2. Now, Yap Chen, before we draw resonance, right? What is this bond? Single or double?
Single.
Single. And what is this bond here?
Double.
Double. Now, because they are resonance structures, we say that 50% of the time, it looks like this. And 50% of the other, it looks like this. Now, what is in between a single and a double bond?
A so-called 1.5 bond?
Yes, right? Single and double, 1.5 bond. Now, here's the thing. Because the bond is 1.5, we say that the bond strength, and before I talk about bond length, guys, I'm going to talk about strength first, okay? Now, because like what Yap Chen said, it is not a single bond, neither is it a double bond. We say that the bonds in benzene is actually a 1.5 cc double bond. And how do we draw that? We draw it like this. Dot, 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 dot. So 1, and this is 0.5. Oops, sorry guys. 1, and that's 0.5. So 1.5 bond. Okay. So Yap Chen, you would think that you would say that it's quite intuitive that the bond strength of a 1.5 bond is in between a single and a double bond.
Yeah.
Right? What about the bond length?
In between as well.
Okay, and before we go into that, right, can you also tell me how is bond length related to bond strength?
Well, the longer the bond length,
Okay.
the weaker the bond strength.
Why?
I mean, it's
How
like
do
a
you-
spring, right? If you keep stretching it, right,
Oh,
if the
yeah.
bond length is very long,
Intuitive.
right, it's
Exactly.
easily broken.
Yes. So, like exactly what he said, the longer the spring, the easier for you to bend that spring. But if the spring is very, very short, then you can't really bend it, right? So, longer the bond length, the weaker the bond. So, here's the thing. Follow through with me. This 1.5 bond, it is stronger than a single bond and weaker than a double bond. Which means the bond length should be just in between both of them. And you can go and think about that. It's not difficult, okay, at all. And that's it. And we're going to talk about additional stability in a bit. Digest this before we move on to the next part.
And now, before the next show starts, let's enjoy an intermission. You'll find our snack bar chock full of good things to eat and drink. Tasty, tempting hot dogs, thirst-quenching...
Okay, so Yap Chen, we just finished the whole idea of the stability bit for benzene, and you look incredibly bored.
Oh, you can tell?
Yeah, man. So do you think it's important?
I mean, it sounds very theoretical. I don't think they'll test it.
I would have thought so too, but do you remember how stunned we were when we saw this question in 2017? And our poor little students were so damn crazy stunned
Yes.
too. We saw this in 2017, and this is what A-level tested, okay? Like guys, literally A-level question, you can go and check it out. So they were testing the hydrogenation of cyclohexene. So you can see here they gave that value here. And then they hydrogenated naphthalene. So it's not even benzene, they went a step further and they tested naphthalene. How insane. And basically the question was asking, if I hydrogenate naphthalene, what do you think the enthalpy change of hydrogenation will be? Okay? So if you guys understood the idea just now, and of course Yap Chen, the moment you look at naphthalene, right? Again, can you see how there are double bonds here?
Yep.
And it's a double bond here.
Yeah.
So in between, you would think there's also a...
Double bond.
Yes, because that's, what's the idea called?
Resonance.
Resonance, exactly, right? So again, there's an idea of resonance stability. So that enthalpy change of hydrogenation, what do you think it is, guys? Think about it, okay? Draw the energy level diagram again and think about it. All right, and that's it. Now, before we end off this video, I need to ask you guys this question. So, of course, organic chem is never complete without talking about nucleophiles and electrophiles, okay? So I'm going to open this to the floor to you guys, and before you guys head for class, and I'm sure you guys are on the way to class now, because I'm sure you guys are watching this video last minute, before you step foot into class, and I want you guys to think about this, and I'm going to open up a fresh sheet of paper. If you look at benzene ring here, okay, again, of course, that circle in the middle, and we have that 6 pi electrons here, right? So guys, I want you guys to think, okay, is benzene a nucleophile, which means electron rich, or an electrophile? An electrophile means, Yap Chen?
Electron deficient.
Exactly, right? So I want you guys to think about this before you step foot into class. One more time. Is benzene nucleophilic or electrophilic? That's it. Okay? I'll end it here. Bye guys.